Talk about entropy and disorder today. For those of you guys here and at home, I went ahead and opened up the assignment that's going to be the remote assignment for tomorrow. That way if you have some extra time today and you want to maybe work on it a little bit, you can. But if not, that's totally fine too. It's not due until Monday, but I just went ahead and opened it so that way you could go ahead and see it if you want. All right, entropy is as a measure of disorder. You remember, I don't know, maybe it was like 2 assignments back, there was like the stack of folded towels and then like just a pile of towels just all tossed in there. And the one that was all just tossed and kind of messy looking, that one had more entropy than the one that was stacked up. We've learned that entropy is a measure of useless energy. There is another way to think of entropy that is critical for understanding life. Okay, maybe not. I don't know why that quit working. I guess I'm just going to underline, I'm not going to circle. Entropy is a measure of disorder. When the rock on the top of the cliff, its energy is all in the form of potential energy. Sitting there, might fall, might not. The energy is due to the rock being in a precise location. The energy is very well ordered since it is concentrated in one spot. It's all right there on that rock. Might fall, might not, but all that potential energy is stored right there. When the rock hits the ground, the energy turns to heat. Remember we said it went over to the edge, hits the bottom, and then the heat spreads out. The same thing as the example when they dropped the rock in the pond, and then the energy in the pond increased because there was still some left, potential energy. It didn't use it all on the way down to the water. That heat becomes broadly dispersed, spreads out. The energy is no longer concentrated at one location, the rock. It's not there anymore. It's spreading out over all of the area on the ground. It is spread throughout the ground, air, and the rock. The energy has become disordered, making it useless to just do work. It's all spread out, so it's not like it's really focused to do one simple thing. While we have seen that entropy increases with the disordering of energy, it also increases with the disordering of matter. Now I can make the stars. I don't know why it wouldn't work a while ago. Increasing disorder results in increasing entropy. So the more disorganized things are, the more entropy there is. This applies to objects, including atoms and molecules. If every atom is locked in a specific location, making it very ordered, entropy is low. So if everything is locked into a specific location, entropy is low. So back to the towels, when they were all stacked up really neat, very low entropy, because it was all very neat and order in its specific stack. If atoms can move around to many places, making them very disordered, entropy is high. Move around makes entropy high. Entropy as a measure of disorder. When these red particles are bonded, they have fixed positions. They are very ordered. The 4 particles act like one large particle. They are more ordered since they all move together. They cannot move in separate locations. Entropy is low. They're all lined up, real specific pattern, tightly stacked together. Entropy is low. When the bonds between them are broken, so now they're not in a certain pattern, they're just kind of all scattered around. The particles are free to move independently. They can go either direction. They have become 4 separate particles again, which can all be in different directions. Less order, high entropy. In general, as particles bond together, reducing the total number of independent particles, entropy is reduced. As they break apart, creating more independent particles, entropy increases. On the left, we have one particle which has less, and on the right, more. More entropy, less entropy. The entropy, I don't know how many times I'm going to say that today. The entropy of the universe increases with time. Its matter and energy becomes less ordered. But life locks a very large number of particles into fixed position. It is very well ordered compared to dispersed matter and energy. Life has low entropy. As an organism grows, its entropy decreases. If entropy is always increasing, how is life, which requires reducing entropy, possible? Now let's think about this for a second. As an organism grows, its entropy decreases. So as it gets larger or grows, its entropy decreases. So let's look back here at our example. Low entropy, so everything is lined up. High entropy, everything is scattered around. So if entropy is always increasing, how is life, which requires reducing entropy, possible? Anybody have a thought? No? Okay, well, let's keep going. For many years, scientists throughout thought the rule of increasing entropy did not apply to life, that life was the exception. So, meaning that it didn't fit the rule. Just us growing did not fit that entropy rule. Now we know that life follows the same rule. As life grows, it becomes more organized and its entropy decreases. Think about as you get larger, think about from a baby even to an adult, you are more organized. Your cells are more developed, your organs are more developed, your brain specifically is more developed. So that would decrease the entropy because you are more focused and you're more in order, more organized than you were as an infant. But life increases the entropy of its environment by an even greater amount. In total, this is the important part right here. In total, the entropy of a living system and its environment always increases, obeying the rule. Accomplishing this requires a consistent source of energy with low entropy. Any thoughts of the source of low entropy energy to support life on the surface of the Earth? Where does the energy come from for life on Earth? Sun. Okay. So, why is the sun then low entropy? Does the sun only focus in one spot, or is it focused all over? All over. So maybe that is part of our entropy. Let's look. The entropy, you okay? The entropy of the universe blank with time. Does it decrease, constant, increase, A, B, or C? Say again? Decrease. Let's look right here. In total, the energy of the living system and its environment always increases. Hold on. Did I read it wrong? Yeah, so increase. Is that right? Okay. The entropy of a growing organism decreases, constant, increases, A, B, or C. So as you grow, you become what?
A.
So I can't hear you.
A.
A. Agreed. The entropy of the environment of the growing organism decreases, constant, increase, A, B, or C. Go ahead, Brooke, what do you think?
Increases.
I agree. 3 molecules combine to form a single larger molecule. What will this do to entropy? Remember that they're lined up together, they're bonded together. Is that going to decrease, no change, increase, A, B, or C? Go ahead.
Decrease.
Decrease, correct. Remember, if they're all broke apart, they're a mess, so that's going to increase it. But if they're in a nice line together, all stuck together, that's going to decrease it. Freezing locks water molecules into fixed positions. As water freezes, its entropy will decrease, not change, increase, A, B, or C. Go ahead, McKenna, what do you think? A? I think you're right. The principle of entropy applies to blank. Only matter, only energy, matter and energy, only life. Go ahead.
C.
C? Correct. All right, and that's it for today. I've already posted your assignment, so you guys have that at home and here.